Now let's explore second-order linear inhomogeneous differential equations, but ones that still have constant coefficients. So by inhomogeneous differential equations, what I mean is that the term on the right-hand side is not zero for these types of differential equations. Instead, you have a non-zero term that doesn't depend on x, but it could depend on t. So how do we solve a differential equation that looks like this? Well, there's generally two techniques that we're going to use. It's the same techniques we used for the homogeneous version of this differential equation. We're going to use guess and check and linear superposition. Let me actually talk about the second one first, the linear superposition. And linear superposition will tell us that the general solution to this differential equation is the sum of two parts. A homogeneous solution, the solution to the homogeneous differential equation, and then a so-called particular solution. So the homogeneous solution we know how to do. That's just setting the term on the right-hand side to zero. That's what we mean by a homogeneous differential equation. And we can solve this by making a standard guess that the homogeneous solution looks like e to the pt for some p. And we get a characteristic equation, which gives us allowed values of p. And then we can write down the homogeneous solution as a sum of two different terms for the different p-values that we got from the characteristic equation. So this is the homogeneous solution, and so that's half of the general solution to the inhomogeneous differential equation, which is nice. So that means we already know how to do half of this. We just solve using the usual technique, forgetting about the term on the right-hand side. Okay, but we need to somehow deal with that term on the right-hand side, and we haven't done that yet. And so that leads to the so-called particular solution. And for the particular solution, we now want to solve the differential equation with that term over there on the right-hand side, so we need to make a different guess. If we make the exponential guess as we did for the homogeneous solution, it's not going to work. So we need to make a different guess. This part can be a little bewildering. What kind of guess should we be making? Well, in general, the general rule is you're going to guess something similar to the term on the right-hand side, the same functional form. So in this case, we had a constant on the right-hand side, so we're going to guess a constant, some undetermined constant right now, and we're hopefully going to determine it in the process of plugging it into the differential equation. We'll look at more general cases in just a little bit and what guesses you should make. But right now, we see that we have a constant on the right-hand side, so we're going to guess something similar, namely a constant, but it's going to be an undetermined constant. I'm just calling it capital C here. So let's plug this into the differential equation. Well, the first derivative and the second derivative of a constant are both zero, so the first and second term of our differential equation just gives me 0 minus 4 times 0. The third term in the differential equation, 3 times x, now becomes 3 times that c, and this must now all equal 6. Well, that tells me I guess 3c is equal to 6, or rather c is equal to 2. Just plugging this back into our particular solution, we find that the particular solution to this differential equation that solves the inhomogeneous differential equation, including the term on the right-hand side, is xp, x particular, of t is just 2, just a constant. Okay, so then the general rule that we said at the beginning for linear superposition is that the general solution is the sum of the homogeneous solution and the particular solution. So I guess we're just going to add these. So it turns out the general solution to this differential equation is c1 e to the t plus c2 e to the 3t plus 2. And you can check by plugging this back into the original differential equation that this is indeed a solution to the inhomogeneous differential equation. It solves this full differential equation that we started with at the top of the page. And it has two undetermined constants, as you would expect for a second-order differential equation. And so the beauty of linear differential equations like this is if you found a solution that satisfies the criteria, it is the solution. So that's the general solution, which is pretty slick. So now let's consider what might happen if we had a more generic term on the right-hand side. So instead of 6, let me say that the term on the right-hand side is r of t, for some function r of t. What are we supposed to guess to solve this particular solution for the differential equation? Well, r of t as a function can take the general sets of forms. And so let's just list a couple of what this function on the right-hand side might look like, and therefore what the guess would be. So we've already seen that if r of t is some constant, then we would guess also a constant. So that's the top line of this table. If r of t on the right-hand side looks something like t, just depends linearly on t, then we would guess something that looks linearly on t. So we're guessing something that looks similar to the function that we had on the right-hand side. In this case, I don't just include a times t, I would include a times t plus b. And that rule holds more generally. So if r of t was, say, t to the 4, then I would need to include not only a term for my guess that looks like t to the 4, but I need to include all lower powers of t to the 4 down to a constant as well. It's annoying that you have to include all of those, but you'll find if you don't include them, then it doesn't work for a solution. So you really do need to include all lower powers, t to the 4 down to a constant, or whatever power of t you happen to have on the right-hand side. If the term on the right-hand side, r of t, is sinusoidal, maybe it's a sine or a cosine, then we're going to guess a combination of sines and cosines with the same dependence. So if I have sine of at, I'm going to guess that the particular solution looks like sine of at or cosine of at. And in general, again, I'll have to have a sum of both sine and cosine. So I'll need to include both of those for my guess. If r of t is an exponential, e to the at, then I'm going to guess something that looks like e to the at, but with some undetermined constant out front. This is called the method of undetermined coefficients, perhaps clearly here because these guesses involve undetermined coefficients, calling them a, b, c, and so forth, that we can determine by plugging the guess of the particular solution into the inhomogeneous differential equation and then solving for those undetermined coefficients. Let's look at another example. Let's look at the example where indeed r of t on the right-hand side is just t. So the guess, according to our table, is we should guess for the particular solution is at plus b. So let's take that as our guess. In order to plug this into the differential equation, we have to take the first and the second derivative of this guess. So the first derivative just gives me a, the second derivative gives me 0. So plugging this into the differential equation above, I get nothing from the second derivative. I get minus 4a from the first derivative term, and then I have plus 3 times my original guess, at plus b, and all of this must equal t somehow. Let me just multiply out that third term, distribute the 3 through, and then kind of group terms. So I'm grouping 3b minus 4a, those are just constants. And then there's a term that looks like 3a times t, so that term depends on t, and this must now all equal to t. A general strategy in solving a differential equation like this is you're going to match powers of t or functional forms on both sides. So, for instance, we see if we want to match both sides of this equation, I need to match the coefficients of the terms multiplying t. So 3a, which is multiplying t on the left-hand side, must equal 1, which is multiplying t on the right-hand side. Well, that's nice. That immediately tells me what a is. So a is 1/3. I can continue matching. On the left-hand side, I have a constant, 3b minus 4a, and on the right-hand side, I have no constant. So it must be that 3a minus 4b ultimately leads to 0. I already know what a is, so I can solve for b in terms of a, and I guess it looks like b is 4/9. So by taking this guess for the particular solution, plugging it into the differential equation, I was able to solve for the undetermined coefficients a and b, found a is 1/3 and b is 4/9. So let me plug those back into my original guess so that I now have my particular solution 1/3 t plus 4/9. The last step in solving this inhomogeneous differential equation wasn't at finding the particular solution. The last step was to write the general solution, which is the sum of the homogeneous solution and the particular solution. So let's do that last step. The homogeneous solution hasn't changed. In fact, it won't change. You can keep adding different functions on the right-hand side, and the homogeneous solution is the same, of course, because the homogeneous solution is setting the term on the right-hand side to 0. So we know that the general solution in this case is the sum of the homogeneous solution, c1 e to the t plus c2 e to the 3t, plus the particular solution, 1/3 t plus 4/9. And there we go. That's our general solution to this inhomogeneous differential equation. And this technique is going to apply more generally. So we're just going to make a guess depending on the R of t we have on the right-hand side. According to this table, or more generally, you're just going to guess something similar to the function on the right-hand side. That's what we're ultimately after. And once you've found the particular solution, the general solution is then the sum of the homogeneous solution and the particular solution.